Alright, I hope you like flow rates as much as I do because we have another problem. You are filling your 1 liter water bottle at a drinking fountain, and the water coming out of the fountain is coming out at a rate of 0.731 moles per second. And you're in a rush, and you only fill the bottle 3/4 full, and only 90% of the water coming out of the fountain actually makes it into the water bottle. So let's see what they want from us in this problem. They want us to calculate the volumetric flow rate of water in liters per second, and they also want us to calculate B, the time we're spending at the fountain in seconds, and finally, part C, they want us to calculate the final mass of water in the bottle in kilograms. And they want us to use the conversion factor for density, 1,000 kilograms per meter cubed. Okay, so let's just make a little visual so we can kind of see what's going on. So we have this little water fountain here, and you have your water bottle over here, and that is 1 liter. And they say we're only filling this 3/4 full. Okay, so that's 75%, or 0.75 liters. Alright, but that's not the volume we're going to be using, because they tell us another thing, that 90% of the volume coming out makes it into our water bottle. So 90% of the volume coming out is equal to our 0.75 liters. Alright, so the volume of water actually coming out of the fountain we can get by dividing this 0.9 over, and the volume is 0.833 liters. And you can double check this for yourself and say, what is 90% of 0.833 liters? And you'll get 0.75 liters. So it checks out. That's just a double check that if 0.833 liters comes out of the water fountain and 90% of it makes it into your water bottle, that'll be 0.75 liters. Alright, so as usual, let's write out what we're given. We're giving the molar flow rate, and we want to get to the volumetric flow rate. But we cannot go directly from the molar flow rate to the volumetric flow rate because we do not have the moles per volume relationship. What we do have, though, is the density, and we can also calculate the molar mass. So what we'll have to do is use the mass flow rate. We'll have to do the intermediate calculation, and we'll be using the molar mass of water as well as the density of water. Alright, so our molar flow rate is 0.731 moles per second. Okay, so we're going to be starting with this. I'll write a new line so we have more room for a calculation. So coming out of the fountain, we have 0.731 moles of H2O per second. And what we're going to want to do is first get the mass flow rate, and we do that with the relationship. For every mole of H2O, there are 18 grams. So we now have the grams per second mass flow rate. And at this point, we'll use our density to get the volumetric flow rate. So we know there are 1,000 kilograms per every meter cubed of water. But instead of writing kilograms, we want to cancel out grams. Let's write 1,000,000 grams per meter cubed. And lastly, we want to get this in liters per second. That's what they asked for. We currently have meters cubed per second. So the relationship there is that there are 1,000 liters in every meter cubed. Okay, so our final units, we have liters second. Our answer is going to be in liters per second. Doing that quick calculation, we get 0.01315. And we started with 3 significant figures, so let's stop at 3. And we can write our final answer with appropriate units. For part A, the volumetric flow rate is 0.0132 liters per second. Alright, and this volumetric flow rate is really useful because you can either get the volume coming out of the fountain given the time, or you can get the time to fill a certain volume. And this is actually what we're doing here. We're given the volume we want to fill. So this is where that 0.833 liters comes in handy. That's the amount of water, the volume coming out of the water fountain. And we have our conversion that we just found in part A, 0.0132 liters are coming out of the fountain every second. So doing that calculation, we get 63.10606 continued, and we see that we have our units second. So writing that out, part B, we have the time, and let's do 3 significant figures. We have 63.1 seconds. Alright, so at this fountain, you're going to be spending a little bit over a minute, which is pretty long. They should really upgrade their fountain system. Okay, so for the last part, part C, which is the easiest part of all. So let's go back to originally. We have our 1 liter container, and we want to fill that 3/4 of the way. So our final volume that we're getting to is 0.75 liters. And we want to convert this into mass in kilograms. Alright, so what is the conversion factor we need? We need to know how many liters there are per 1 meter cubed, and there are 1,000. And we also need to know the kilograms of water per meters cubed, which we know we've used that several times now, 1,000 kilograms per meter cubed. And when you look at that, there's 1,000 on the top and 1,000 at the bottom. So for part C, our M, our mass, ends up being the same, 0.75 kilograms. So an important thing to note for water is that most of the time 1 kilogram is approximately 1 liter. Alright, thanks for sticking through the video and making it all the way. Keep up the great work.